Now let's talk about field axioms. The axiom itself is something that you must accept it without proof. So, yeah, you just cannot ask me what is the proof, sir. It's just something that you need to accept, just like postulate. Okay, and it is a starting points to work with numbers. It means that we have to establish a ground rules about how these numbers interact to each other. But for this part, we will focus on two operations: addition and multiplication. Okay, so there are 11 field axioms that we will learn for this today. So the first one is the commutativity, and you have already learned this one before. Previously, you are familiar with the property, commutative property. So the first two field axioms are commutativity for addition. Okay, so in variables, if we say it, this is like the one that we displayed. Commutativity, how to remember it, it's the origin is from commute. So commute back and forth. So you change the order. So whenever you change the order, x plus y plus x, it's just the same. It doesn't change the value. It doesn't change the rules. It's fine. Okay, as long as you have addition with you. So if I apply it in numbers, well, 4 plus 7 is 11. So if I change the order 7 plus 4, it's still 11. So it's safe for us to do the commutative for addition. How about for multiplication? It's the same. So in variables, the language is if every a times b will be it will be equals to b times a. So in numbers, yeah, 4 times 7, 28. So it be equals to 7 times 4? Yeah, of course, it's still 28. So the next two field of axioms are associativity for addition. Associativity origins is from associate. So you can associate the first two parts, or you can associate the last two parts, or you can associate the others as long as it is addition. The language in variables, if there is an x plus y plus z, it means if you want to sum the first two variables, x plus y, and then you add it by z, it will be just the same if you add x by the sum of y plus z. Okay, in numbers language. So if I have 3 plus 5 plus 7, which is 15. So if I sum 3 plus 5 first, which is 8, and then add it by 7, I will have 15. But it will be just the same if I add 5 plus 7 first, which is 12, and then add it by 3. Okay, so it's just the same. So it's safe for you to associate which one first as long it is addition. And how about multiplication? It's the same. It's the same. In variables, if I have a times b times c, I can associate a with b first and then I multiply it by c, or I can multiply b by c first and then I multiply the product by a. So in the language of numbers, so if I multiply 2 times 3 times 4, which is 24, so I can multiply 2 times 3 first, which is equals 6, and then multiply by 4, 24. Or I can multiply 3 times 4 first, which is 12, and then multiply by 2, still 24. So in multiplication also it's safe for you to do associativity for multiplication. Okay, so we have already covered four field axioms. The fifth is distributivity. So this one is will be applied only for one variation, only for multiplication over addition. Okay, so well you have been familiar with distributivity. Uh, so in variables, if I say that a times x plus y will be distributed. You can distribute the a into the x and y. Okay, so uh, yeah, this will be equal with the order operation. So this will not violate the order operation as long as since the order of operations says that you have to give prioritize to the everything inside the parentheses and then you multiply it by a, right? But by doing this axiom, it it won't against the rules of order operations since you can do the multiplication over addition. So in numbers, if I say that I have to multiply 3 plus 2, 3 times 2 plus 4, it means originally I have to multiply 3 plus the sum, which is 6. 3 plus 3 times 6. I'm so sorry, I'm just 3 times 6 is 18. This is from the left part, right? So is it the same with the right part if I distribute 3 over the addition? So 3 times 2 plus 3 times 4. 3 times 2 is 6 plus 12. 6 plus 12 is 18. So 18 on the left side equals 18 on the right side. So it is just the same. It means you can apply distributivity multiplication over addition. It is safe. Okay. Yeah, sorry. Let me just go back to that. Yes, you can see it. Okay. So the sixth and seventh field of axioms is unique identity element. Okay, what is unique identity element? There are two. First of addition, the unique identity element of addition. If I ask you what is the unique identity element of addition, you just answer it. It is zero. Okay, why? Because all numbers, if I add it by zero, it will be the number itself. Okay, so if any sets of any numbers from any sets of numbers, if you add it by zero, it will be the number itself. That's why the unique identity element of addition is zero. So the unique identity element of multiplication, what is the number? If I multiply any numbers, it will be the number itself. So it must be one, right? Not zero. So, okay. So if I multiply, for example, a times 1, it will be still a for any numbers from any set of numbers. Okay. So what is it? The eighth field of axiom are inverse. The first one is additive inverse. So the definition of additive inverse is if a number you add it by the its additive inverse, it will be equal to the identity element. So if you recall back to the previous one, the identity element of the additive of addition is zero. Identity element of addition is zero. So it means if a number you add it by its additive inverse, it must be zero. It means, for one example, the additive inverse of 9 is negative 9. Why? Because if I add 9 by negative 9, I will have the identity element of addition, 0. So for multiplicative inverse, the definitions is almost the same. See, a number, if it is multiplied by its multiplicative inverse, it will be equal to the identity element of multiplication. The identity element of multiplication is 1. So what is the number? What is the multiplicative inverse? If you multiply it by number, it will becomes 1. The multiplicative inverse of 9 is 1/9. Since if you multiply 9 by 1/9, it will be equal to 1. So if I give you another example, what is the additive inverse of 100? The additive inverse of 100 is negative 100. Okay, since 100 plus negative 100 equals 0. What is the multiplicative inverse of pi? The multiplicative inverse of pi is 1 over pi. Okay, since pi times 1 over pi equals 1. That's how you name it. So yes, you maybe get a hint about what is the other name of additive inverse. The other name of additive inverse is the opposite, and the other name of the multiplicative inverse is reciprocal. Yeah. And then, yeah, we have covered 9 field axioms, so we just have to deal with 2 more, which is a little bit new, but actually it's the concept is very simple, closure. The first one is close under addition. What is close under addition speaks about? The statement is, you can see it on the textbook, but uh, x plus y equals z. If x plus y equals z, so if I pick a set of numbers, for example, real, if x and y are real numbers, then z, the sum, will also real numbers if the set of numbers obey the close under addition. So it must be another real. And z, the sum, is unique. Is unique means it's only one possibility of answer. So for example, if I add a real number 4 plus real number 2.5, okay, if I add 4 plus 2.5, it will be equal to 6.5. 6.5 is not a real number, and you don't have any other possibility of answer aside of 6.5. That is close under addition. So the same with close under multiplication. If x times y equals z, and I pick another example from real number, if x and y are real numbers, then z, the product, must be also real number. And z is unique. It means there is no other alternative. So for example, if x is, so if I multiply 5 times square root of 5, 5 times square root of 5. 5 is real number. Square root of 5 is real number. The result is 5 square root of 5, another real number. And it's only that 5 square root of 5 as your answer. There will be no other answer. That is close under multiplication. So yeah, after we covered all 11 field axioms, so let's go to the field. Field, it it is a name, it is a situation if a set of numbers obey all 11 field axioms. So if all 11 field axioms can be applied to a set of number, so that set of number is a field. So this is all 11 that you can see on the right side. The sets of numbers must obey all of it. So if only one field of axioms they cannot obey, that set of numbers is not a field. So I will give you example. You can read thoroughly on the textbook. But for example, if I use set of number real, okay, so I need to check. The analogy is here. If this world knows only real numbers, okay, they only know real numbers, they don't know any other numbers, which is of course imaginary. Imaginary is the opposite of real numbers. I mean, is other thing that real numbers. So if this world only know real numbers, we haven't known about complex number. So will these all 11 field axioms show or involve all numbers that are from real numbers? For example, commutativity for addition. Will a plus b equals b plus a involve real, can be applied to real numbers like square root of 5 plus square root of 7 equals square root of 7 plus square root of 5? Yes. So all of it can be applied on real numbers except except this one, multiplicative inverse. If you can remember, multiplicative inverse speaks about the reciprocal, except for 0. So there is only one problem here for real numbers. Well, we can say it is a field as long as we don't include 0. So there is an exception. Why 0 cannot be applied on multiplicative inverse? Multiplicative inverse, reciprocal. So if it is 0, the reciprocal is 1 over 0, which is undefined. So uh, it cannot be applied for 0. That's how you prove it. So let's just pick another set of numbers. So if I pick radicals, okay, is radical or is radicals or radicals are filled, it means I need to check one by one to these 11 field axioms, and can all of the numbers involve radicals only, not outside radicals? Okay, the answer is no. since radicals cannot obey the last one, close under multiplication. So if I recall back, close under multiplication, if I multiply x times y equals z, if x and y are radicals, okay, the z must be also radicals and unique. That is close under multiplication. So is that it can be applied for all radicals? No, sadly. So if I multiply square root of 3 times square root of 3, square root of 3 is a radical, and square root of 3 is another radical, it will be equals to 3. Square root of 3 times square root of 3 equals to 3. The result, the product is not radical. It is an integer. It is a real, it is a rational number. Therefore, it comes up a number that the radicals doesn't understand. So it doesn't obey close under multiplication. Therefore, radicals is not a field. That's how you prove it. And let's see the last one. Okay. So how about digits? If I pick set of number digits, is it a field? So let me show you how to check one by one. Commutativity of for addition, digits will obey that. Okay, of course, 1 plus 2 will be equals to 2 plus 1. Overall, I think all set of numbers won't violate this one. Commutativity for multiplication also, associativity, distributivity, no problem. Additive inverse, okay? Now this is a problem, okay? Will the additive inverse of a digit will be another digit? That is how you check the is it a field or not, since it has to obey the field axioms. So all the axioms that we check, it doesn't come up with another numbers outside of digit. So the additive inverse is the opposite, right? If I pick any digits, for example, 3, the additive inverse of 3 is negative 3. Negative 3 is not a digit. Therefore, this one fail. Multiplicative inverse. Multiplicative inverse is also fails. Since if I pick a digit 5, the multiplicative inverse will be 1/5. It's not a digit. So already 2, it violates. And then unique identity, usually no, because unique identity element of addition will always 0 for any set of numbers. This one you also 1 always, so it won't be violated. Close under addition, okay, will if I add a digit with a digit, okay, will the sum also a digit for all digits, okay? Well, if I pick 2 as a digit plus 3 as a digit, yes, it equals 5, another digit. But you have to check all possibilities of digits. Will it comes, will the sum will also consistently digit, which is not. So if I pick a digit 8 plus 9, also a digit, the sum will be 17. It's not a digit. Therefore, it violates close under addition. Okay. And how about close under multiplication? Yes, of course. Obviously, it violates also, since if I pick a digit 5 multiplied by a digit 6, the product will be 30. So, yeah, it violates 4 field axioms. It means digits is not a field. Again, a set of number will be a field if it obeys all 11 field axioms. If just at least one of it cannot be applied, that set of numbers is not a field. Thank you for listening. Goodbye.